Welcome. Today we are going to study the fifth chapter, final module. In this module, we shall study multiple integrals. In the earlier four modules, we studied mainly double integrals. Today, we shall extend our ideas to higher dimensions. Before entering into the discussion for multiple integrals, we shall discuss two examples from double integral. While dealing with problems on double integral, first, we considered functions which were defined over rectangular domains, then we shifted to arbitrary domains with some conditions imposed over them. In the following example, we shall show that we can divide the rectangle Q in some other fashion different from subrectangles to make our calculations easier. We are to evaluate over a rectangle Q, that is Cartesian product of 0 to pi and itself, box x plus y dx dy, where box t denotes the greatest integer contained in T. For the sake of convenience, we divide Q into the following regions. A1 is collection of all xy such that x plus y is greater than or equal to 0 but strictly less than 1. Similarly, we define A2, A3, A4, A5, A6 and A7. One can see the regions from the attached figure. Clearly, f reduces to a constant over each region ai. Moreover, for each I, fxy is equal to I minus 1 for every xy in ai. Keeping this in mind, we formed this adjacent table. So, for each table, we found the area and the value of f over that region, and finally, we calculate the value of the integration. Next example, let Q be the Cartesian product of two bounded closed intervals AB and CD, and f from Q to R be both bounded and integrable. We further assume that for each xy in Q, we can express fxy equal to gx into hy, where g from AB to R and h from CD to R are bounded functions. Our second assumption is that both the integrals integral a to b gx dx and integral c to d hy dy exist finitely. Then for every fixed y from bounded closed interval with endpoints c and d, we find integral a to b fxy dx equals integral a to b gx hy dx equals hy integral a to b gx dx. Similarly, for every fixed x from bounded closed interval ab, integral c to d fxy dy equals integral c to d gx hy dy, and it is equal with gx times integral c to d hy dy. Integrating all the sides of the first relation with respect to y or the second one with respect to x, by virtue of the theorems we discussed, we find that double integral of f over q equals with integral c to d hy integral a to b gx dx dy. This equals with integral c to d hy dy multiplied by integral a to b gx dx. Now we are in a position to introduce the notion of multiple integrals. For multiple integrals, the domain of integration is a bounded and closed set in Rn, and the integrand is a bounded scalar field defined on that set. Let us consider first a collection of bounded closed intervals II. For every I, this is bounded closed interval with endpoints ai and bi, where ai is less than bi, and I runs from 1 to n. That is, we assume that all the intervals are non-degenerate. That is, none of them is a singleton set. Let I be the Cartesian product of these intervals in their natural order, that is I equal to I1 cross up to In, and clearly it is a bounded closed set in Rn. Such a set is called a n rectangle. Now let f from I to R be a bounded function. For every interval II, we consider a partition Pi equal to Ai equals x0i less than x1i continued up to xnii, which is Bi. This induces a partition P equal to P1 cross P2 up to Pn of I. Let us denote Q J1 J2 up to Jn equal to Cartesian product of the subintervals first xj minus 1 1 xj1 1, then xj2 minus 1 2 xj2 2 up to xjn minus 1 n xjn n. Since f is bounded over I, it is bounded over each q j1 j2 jn because all q j1 j2 jn are subsets of I. Here xj1 is in P1 and so on. Let capital M j1 j2 up to jn is defined by the supremum of f x1 x2 up to xn, where x1 x2 xn is arbitrarily chosen from q j1 j2 jn. Similarly, we define small m j1 j2 jn with the help of infimum of values of f over q j1 j2 jn. Clearly, small m lesser equal to small m j1 j2 jn lesser equal to capital M j1 j2 jn lesser equal to capital M, where capital M is the supremum of f over I and small m is the infimum of values of f over I. We also denote V j1 j2 up to jn equal to the n measure of j1 j2 jn's in subinterval. For any partition P, the norm of P is denoted by the symbol norm P and is defined to be the maximum of n measures of the subrectangles formed due to the partition P. We form the sums UFP equal to summation over j1 j2 jn, capital M j1 j2 jn, capital V j1 j2 jn, and LFP equals summation over j1 j2 jn, small m j1 j2 up to jn, V j1 j2 up to jn. These are called the upper and lower Darboux sums of f with respect to the partition P. If capital V is the n measure of I, that is, it is B1 minus A1 multiplied by B2 minus A2 up to Bn minus An, then it is easy to verify that small mv lesser equal to LFP lesser equal to UFP lesser equal to capital M capital V. This implies both the lower Darboux sum and the upper Darboux sum are bounded. Refinement of a partition can be defined exactly in the same way we defined earlier for double integral and for Riemann integral. The proofs of the following propositions are similar to those we did for double integrals. First one, if P dash is any refinement of P, then LFP lesser equal to LFP dash and UFP dash lesser equal to UFP. This implies by refinement the lower sum increases and the upper sum decreases. It may not be strictly. Second proposition, any lower sum can never exceed any upper sum. Let we use the n many integral signs over I and then put a line below f to define supremum of LFP where P comes from collection of all partitions of I, and then we define another quantity which we denote by n many integral signs. Put I below it and put a bar over it and apply it over F by infimum of UFP, where P is any partition of I. We call them the lower integral and the upper integral of F over I. Clearly here Pi denotes the collection of all partitions over I. We use n many integral signs to mean that it is an n-fold integral. If the upper and lower integrals of f over I coincide, then we say that f is integrable over I. The common value is said to be the integral of f over I. We denote this by symbol writing n many integral signs over I and then f. We call it the n-fold integral of f over I. Now we mention some results. These results also hold for multiple integrals. We proved these results for double integral, and the proofs are similar to the corresponding proofs of double integral. First one, f is integrable over I if and only if, corresponding to every arbitrary positive epsilon, there exists a partition P such that the difference between the upper Darboh sum of f with respect to p and lower Darboh sum of f with respect to p is less than epsilon. Clearly, this quantity is non-negative. Second proposition, f is integrable over I if and only if, corresponding to every epsilon positive, there exists a delta such that for every partition p, norm p less than delta implies UFP minus LFP less than epsilon. Third proposition, if f is continuous over I, then f is integrable over I. Fourth one, if the collection of all discontinuities of f over I is a set of content 0 in Rn, then f is integrable. The above notion of integrability can also be alternatively defined using the concept of step functions. We did the same for Riemann integral and also for double integral. The n-fold integral of a step function is defined exactly in the same manner. For any bounded function f from I to R, we consider the collection of all step functions L and U on I, satisfying Lx less or equal to Fx less or equal to Ux for each x in I. If there exists a unique k such that for every pair of step functions L and U satisfying the above inequality, we find integral for step functions over I for L less or equal to k less or equal to integral for step functions for U over I. Then we say that f is integrable over I, and we write n integral of f over I equals k. It is needless to mention that above two notions are equivalent. If we assume one of them, we can deduce the other. The third equivalent notion is to construct the Riemann sum summation j1 j2 jn f at the point j1 j2 jn multiplied by v j1 j2 jn. Notations are discussed in Darboh sum, and we consider the limit of this sum as norm of p tends to 0. If the limit exists, then its value is called the integral of f over I. It can be shown that this notion is equivalent to those we discussed earlier. Finally, let Q be a bounded and closed region in Rn and f is a scalar field defined on Q. To consider the integrability of f over Q, we consider any bounded closed n rectangle Q tilde containing Q. We define another function f tilde over q tilde real valued as follows. F tilde x is defined as fx if x is in q and 0 if x is in q tilde but not in q. Clearly, we can consider f as the restriction of f tilde over the set q. Now, if f tilde is integrable over q tilde, we say that f is integrable over q and we define the n-fold integral of f over q is the n-fold integral of f tilde over q tilde. We cite an example. Let us evaluate the value of the triple integral dx dy dz over the set S, where S is a solid sphere of radius a and centered at the origin. That means, over the given set S, we are integrating the constant function whose value is 1. Solution. We know the given solid sphere S is given by collection of all x, y, z in R3, where x square plus y square plus z square less or equal to a square. Let S1 be the solid portion OABC of the solid sphere S defined by S1 is the collection of all x, y, z in R3 such that x square plus y square plus z square less or equal to a square, where x, y, z all are positive but are below a. That means we consider the portion of the sphere which is in the first or positive octant. We have shown it here. Now, it is clear that the volume of the entire sphere S is 8 times volume of the part S1. Therefore, we can write triple integral of dx dy dz over S equals 8 times triple integral over S1, and this equals 8 times integral x equal to 0 to a, integral y equal to 0 to square root a square minus x square, integral z equal to 0 to square root a square minus x square minus y square dz dx dy. Hence, triple integral over S dx dy dz equal to 8 times integral x equal to 0 to a, integral y equal to 0 to square root a square minus x square of square root of a square minus x square minus y square dx dy. And this equals with integral x equal to 0 to a, integral y equal to 0 to square root a square minus x square root a square minus x square minus y square dy, and this integral is integrated with respect to x. So, this equals 8 times integral x equal to 0 to y of y by 2 square root a square minus x square minus y square plus a square minus x square by 2 sin inverse y by square root a square minus x square evaluated with respect to lower limit y equal to 0 and upper limit y equal to square root a square minus x square. And we find that this equals 8 times integral x equal to 0 to a square minus x square by 2 times pi by 2 dx. And finally, we find that it equals with 4 by 3 pi a cube. Now, we are going to consider the change of variables for multiple integrals. The formula for change of variables in an n-fold integral is similar to that we deduced for double integral. We shall first mention the result for triple integral and later for an n-fold integral. Theorem. Let S denote a bounded rectangular parallelepiped. We consider an invertible transformation f described by the maps UVW from S to R given by U is UXYZ similar for V and W, whose inverses are given by x equal to x UVW, y equal to y UVW and so on. Let Fs is equal to T. We further assume that x, y, z have continuous partial derivatives when considered as functions of u, v, w. Secondly, the Jacobian determinant del xyz del u, v, w defined with the help of the determinant del x del u, del x del v, del x del w. This is the first row. Then del y del u, del y del v, del y del w. This is the second row and final row. Del z del u, del z del v, del z del w is non-zero almost everywhere on the set T. Then triple integral of f over s equals with triple integral of f over t. Now, f is considered as functions of u, v, w multiplied by modulus of the Jacobian determinant du, dv, dw. Clearly, the above result can be extended to the case when S is any bounded region in R3. While discussing the geometrical interpretation of the change of variable formula for double integrals, we found that the Jacobian determinant was the scaling factor or magnification factor for areas. Clearly, in case of triple integrals, the Jacobian determinant plays the role of magnification factor for volumes. We can denote this map by f u v w equal to x u v w, y u v w, z u v w. Then del f del u equal to del x del u, del y del u, del z del u and so on. Dealing with similar argument, we find that a rectangular parallelepiped of dimensions del u, del v and del w is transformed into a parallelepiped like figure bounded by surfaces and having volume modulus of del f del u, del f del v and del f del w. These three are three vectors. We consider their box product multiplied by del u, del v, del w, where we find that the box product del f del u, del f del v, del f del w equals del f del u dot del f del v cross del f del w, and it equals with the Jacobian determinant del xyz del u v w. And while considering the change, we consider the modulus of this quantity. Now, we mention two important transformations which we use regularly. First one, from rectangular Cartesian coordinate system to cylindrical polar coordinate system, and second, from rectangular Cartesian coordinate system to spherical polar coordinate system. First, we discuss the transformation from rectangular Cartesian coordinate system to cylindrical polar coordinate system. This system is expressed by order triplet xyz goes to order triplet r theta h, where x as a function of r theta h is expressed as r cosine theta, y as r sine theta and z is h, where r or h are any real number and theta we consider from the bounded closed interval 0 to pi. We find that the Jacobian determinant for this transformation is del xyz del r theta h, and after some calculation we can find that this is nothing but r. Clearly, this Jacobian vanishes only at the origin, which makes a set of measure 0. Thus, for any scalar field f integrable over S, the rule of change of variables is given by triple integral of f over S equals triple integral of f considered as a function of r theta h, that is f of r cos theta, r sin theta h, r dr d theta dh, and integrated over t. Here we use the condition that r is non-negative. Next, from rectangular Cartesian coordinate system to spherical polar coordinate system. This system is expressed by order triplet xyz goes to order triplet r theta phi, where x is r cosine theta sin phi, y equal to r sin theta sin phi, and z equals r cosine phi. Here r is any real number. We consider theta from bounded interval 0 to pi, open at the right end and closed at the left end, and phi from bounded closed interval 0 to pi. We can check that the Jacobian determinant for this transformation is del xyz del r theta phi is minus r squared sin phi. One can easily check that the Jacobian vanishes on a set of measure 0. Thus, the law of transformation is given by triple integral of f over s equals triple integral of f r cos theta sin phi, r sin theta sin phi, r cos phi, modulus minus r squared sin phi dr d theta d phi over the region T. Finally, we state the formula for an Enfold integral. Theorem: let S denote a bounded region in Rn. We consider an invertible transformation capital F described by the maps u1 u2 un from S to R given by u1 equal to u1 x1 x2 xn, u2 equal to u2 x1 x2 up to xn, and similarly going up to un, whose inverse map is described by the equations x1 equal to x1 u1 u2 un and so on. We further assume that all the partial derivatives del xi del uj are continuous. Here we have n square partial derivatives of this kind. If the Jacobian determinant del x del u, that is del x1 x2 xn del u1 u2 un, which is nothing but determinant of del xi del uj, I and j both run from 1 to n, is non-zero almost everywhere on the connected region T equal to Fs, then integral of f over s equals integral of f x1 x2 xn, but considered as function of u's, multiplied by modulus of del x del u du1 up to dun over the region T. We cite an example here. Let us evaluate triple integral dx dy dz by 1 minus x square minus y square minus z square over the portion of the sphere x square plus y square plus z square equal to 1 lying in the first octant, that is in the octant where all the coordinates have non-negative values. To make the solution easier, we consider the transformation x equal to r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta, where r is from bounded closed interval 0 to 1 and theta and phi from bounded closed interval 0 to pi by 2. We find that the Jacobian determinant del xyz del r theta phi equals r squared sin theta. Therefore, the required integral is 1 by root over 1 minus r square modulus of the Jacobian determinant del xyz del r theta phi dr d theta d phi equal to, we calculate the integral and find its value as pi square by 8. Finally, we discuss the geometric interpretation of the double integral. Our intention is to study the geometric interpretation for a multiple integral. For obvious reasons, only two cases can be considered. First, when the scalar field is defined on a subset of R, that is a Riemann integration, and secondly, when the scalar field is defined on a subset of R2, that is a double integral. The first one being obvious, we know whenever we consider Riemann integral, the geometric interpretation is to find the signed area bounded by the graph of the function to horizontal lines and the positive x-axis. Now we discuss geometric interpretation of the double integral. Our intention is to study geometric interpretation of multiple integrals. For obvious reasons, only two cases can be considered. First, when the scalar field is defined on a subset of R, that is, whenever we consider Riemann integral, we know in this case the geometric interpretation is that we evaluate the signed area bounded by the graph of the function to vertical lines corresponding to the limits of integration and x-axis. Second, whenever the scalar field is defined on a subset of R2, we discuss it here. Let Q be the Cartesian product of two bounded closed intervals AB and CD. So, this is a rectangle in R2 and f from Q to R be a continuous function. So, clearly it is bounded and also integrable over Q. We further assume that for every fixed y from CD, the integral a to b fxy dx exists, and for all fixed x from bounded closed interval AB, the integral c to d fxy dy exists. Then the following formula provides us a method for calculating the double integral of f over q in terms of two successive one-dimensional integrals. Double integral over q fxy dx dy equals integral c to d integral a to b fxy dx dy, and double integral of f over q equals with integral a to b integral c to d fxy dy dx. Let fxy be non-negative for all xy in Q. As we assume that f is continuous, let S be the solid in R3 enclosed by the rectangle Q, the planes corresponding to x equal to a, x equal to b, y equal to c, y equal to d, and finally the graph of f, that is the surface given by z equal to fxy as shown in the adjacent figure. We shall calculate the volume of this solid S and see what exactly this volume represents. It is evident that for every fixed y from bounded closed interval CD, the integral ay equal to a to b fxy dx represents the area of the cross section of the solid S cut by a plane parallel to the z plane. We have shown it in the figure. Now, this cross sectional area ay is integrable on bounded closed interval CD, and the value of the integral c to d ay dy gives the volume of the solid S. Thus, the volume of S equals integral c to d ay dy, which is integral c to d integral a to b fxy dx dy equal to double integral over q fxy dx dy. Hence, the double integral of f over the rectangle Q, that is, double integral of f over Q can be geometrically interpreted as the volume of the solid S enclosed by the rectangle Q, the planes x corresponding to x equal to a, x equal to b, y equal to c, y equal to d, and the graph of f, that is the surface given by z equal to fxy. Thus, in this module, we introduced multiple integrals, we studied their definitions, and then transformation formula, that is method of substitution, and finally, we studied the geometric interpretation for double integral. We conclude here.